Now I'd like to present you Professor Hamdi Dibeklioğlu from Bilkent University. Read his bio. He's an assistant professor in the computer engineering department of Bilkent University. He's also a research affiliate with the pattern recognition and bioinformatics group of Delft University of Technology. He received a PhD degree from University of Amsterdam in 2014. Before joining Bilkent, he was a postdoc at Delft, a visiting researcher at Carnegie Mellon, University of Pittsburgh, and MIT. His research focuses on effective computing, computer vision, and machine learning. He is a member of program and organizing committee of several top-tier conferences in these areas, and serves as an associate editor for IEEE Transactional Effective Computing. Earlier, he served as a guest editor for Springer Journal on Multimodal User Interfaces, Frontiers in Computer Science, and Frontiers in Computer Science. He has received the Outstanding Young Scientist Award of Turkish Academy of Sciences in 2022, the Young Scientist Award of the Science Academy Society of Turkey in 2003, the Research Incentive Award of the Bekir Mustafa Parlar Foundation in 2020. So I have known Hamdi for quite a long time from CMU and
10 years, maybe.
Like 10 years. So I've been into his really interesting research, which involves humans, computer vision, machine learning. So with that, without further ado, I'd like to leave the stage to him. Thank you.
Thank you very much. Thank you very much for the invitation, first of all. It's a very nice environment. I really like that. I haven't visited here earlier. Today I'm gonna talk about multimodal analysis of human behavior. Of course, computational analysis of human behavior, but I don't want to add it explicitly. My background is mostly computer vision. Like if we go back to, masters and PhD, then it turned into machine learning. But nowadays we are analyzing human behavior based on audio, facial expressions, posture, voice, also like the transcribed speech. So machine learning is getting an era where you model everything all together. So if we have data, we would like to use them all. Okay. So today, first, I'm going to give you a very short overview regarding such ideas. Then I'm going to cover 3 topics. First one is assessment of psychology, psychopathology, mostly depression analysis. Then I'm going to talk about a bit deception detection, and lastly, estimation of personality traits. Maybe it would be more interesting in terms of human-robot interaction. Okay, so when we say behavior analysis, we can consider lots of tasks, right? So a task nowadays is based on your imagination, nothing else. I mean, you can just start another small area in your field. Like basically in behavior analysis, we can talk about deception detection or personality analysis, or again psychopathological assessments, or even preference or appreciation recognition. Even though spontaneity detection, like we can basically talk about this preference based on your behavior. Let's say I have a food company. I would like to have a new product on the market, and it is not that easy. Well, we have the idea like, okay, they produce this thing and put it on the market. It really doesn't work like that. They have actually versions of products, then they have lots of experiments, human experiments, like appreciation tests, evaluations, and so on. And at the end, they choose one of the many versions of that product. And they explicitly use this visual analysis and so on. So we had such studies in earlier years in the Netherlands, especially. So this is in use. What else? Appreciation, for instance. Not only preference, but appreciation. We have algorithms, we have methods, for instance. When you're playing a game, it's analyzing your expressions, your behavior, and tries to understand if you like the agent's pattern and kind of updating the model based on your behavior. What else in spontaneity, for instance, through your behavior in earlier years, for instance, maybe this slide would be a better example. We were mostly talking about emotional expressions, maybe facial action units, and we were trying to connect all the behavioral tasks or other computational tasks on such findings, like we see some surprise, we see some happiness, or such action units, so we can say that they like it or not. Okay, so in earlier years, it was mostly on the analysis of expressions, and we were trying to connect the tasks to expressions. But this was kind of an early approach. It wasn't working that well. Why is that? Let's say I eat something. Am I really liking it or not, for instance? If I'm smiling, does it mean that I like it? Not at all, right? So you're not smiling when you're eating. Like you're not laughing when you're eating. So you need to train your models. You need to try to learn the behavior based on the tasks. You cannot connect emotional expressions to the tasks directly. So action unit recognition is another way of doing it. So you can have like around 40 different muscle contractions. You can detect them, and you can also analyze their amplitudes. Based on that, you can talk about it, but still this is a high-level representation. Instead, nowadays, we prefer to have all these end-to-end systems, right? So I have the raw data, like whatever modality signals I have, and I would like to have a big model which tries to learn what's happening there instead of connecting these intermediate representations. So how about other modalities than human behavior? So basically, voice, right? So the first thing maybe after facial expressions, my voice is important. I may talk completely differently right now with the same sentences, right? I can change my voice, then you'll understand, he's not happy. You know, like, oh, he's super happy, whatever. Speech content. I mean, I can easily extract the content of my speech, and I can do some language modeling on top of this. I can track and analyze posture, right? This may be head pose, body pose, and all other signals, okay? I may even use physiological signals. But in the meantime, I can use different representations of a specific modality. These are also different modalities. Okay, what does it mean? For instance, from speech content, I can extract sentence embeddings or like the text representations based on an emotional model. So it tries to understand the representation based on emotions. I can extract another representation, which is mostly on a generic language model. So it is more about the content. I can have another text model, which gives me feeling about the behavioral representation, and I can use them all together. Even only from text, I can have a multimodal system. Let's have a look at the example of psychological assessment. Task-wise, depression assessment is a very active topic in affective computing, in human behavior analysis. Many of the symptoms of depression are observable through expressions and demeanor. So it's you see the patterns, okay? So kind of being not very social, slowing down, and so on. So depression may also affect pause, for instance, or expression dynamics, like the temporal changes. Textual behavior is very clearly different in a depressive content of speech or a normal content of speech. And another thing regarding depression is current diagnosis of depression is almost completely on self-reports. So when you are being assessed for depression, what happens is that you go there, you get an interview with a psychiatrist based on some questionnaire. Okay, so you have a discussion, you're being asked some questions, you answer them, you get some score. Based on even your expressions and behavioral dynamics, they have some notes. And at the end, you get a score. And we have cutoff values. So if your score is higher than that, they say, well, you're in depression, or you may be told like
while you were in depression, you're getting better, and so on, based on the cutoff values. So this thing is working, it's in use, but it is also kind of not very objective, right? So if you change the hospital, your results may differ. If you change the country, your results may differ. This is not significant, maybe, but if you're very close to cutoffs, it may be a problem. So that's why kind of automatic depression or psychopathology assessment is a good tool even for psychiatrists and experts in the first place. The idea here is not like okay, we stop seeing doctors and using this. No, this is kind of an additional expert. Imagine you have a screen next to the expert. They're getting a second idea from that analysis. Our automatic analysis is not error-free after all, right? But it is objective. So if you do if you apply the same behavioral patterns to that analysis, you're going to get the same result even in China, even in Turkey, or in US. It is objective. That's the main benefit. So this is a relatively old study. We had a study with other researchers in Carnegie Mellon. So this study is based on a clinical data set. So we have a data set, complete clinical data set. People are actually undergoing depression treatment, okay? And for some durations, after every duration, they have another interview. We observe the change in expressions, head pose, and also voice. And at the end, the thing I would like to show here is, this is an early trial of deep learning methods. Huh? So nowadays, everything is like by default deep learning. So here we were using just denoising autoencoders. I'm not sure if you're all familiar with such things, but general idea, I'm trying to learn a nice representation. And the trick here is, I have some representation vector. I feed it to some vector, some model. This model first mess up that data. Okay, so it deletes some content of it. Then it tries to learn some representation which can reconstruct the original data. So I am providing basically model a corrupted set of values, and I'm trying to obtain the original set of values. So this is the basic idea of denoising encoders. And if you do it again and again for every time, let's say you learn a representation, this time you get that representation, delete some values, and feed it to another denoising model, and you do it again and again, you have a deep model. So this is stack denoising autoencoding. Okay? At the end, you actually get a very powerful representation. So it is compact in terms of dimensionality, but it is also very representative. So we were using such a representation learning, and then with these, we don't even use the appearance completely. We do facial tracking. So we are only looking at the landmarks. You may ask why. This is mostly because of NIH rules. Okay, so in this project, it is even really hard to get this data in research. And it is sensitive data. You cannot just share or you cannot just use the data of psychiatric patients in research. And during this IRB and ethical permission stages, we are asked to have really confidential analysis. So we are using only landmarks and head pose angles, like in 3 dimensions. In addition to this, with the audio, again, we only use switching pause duration. What is that? Okay, the expert is asking, or psychiatrist is asking some questions, and then I start answering. This turn duration, okay, like how much time is kind of empty there. Nobody is talking. And we use the fundamental frequency. It's kind of, you can think it as like your average voice pattern, let's say, spectral voice pattern. So if you're happy, whatever you may observe higher frequencies, otherwise it's going to go down, basically. And after all, altogether, we use these representations in a temporal manner. So for whole video, we estimate only 1 depression score. Okay, so it's not like frame by frame analysis. We are looking through all dynamics. How were we doing it at that time? I'm going to show it next, but it was like kind of earlier models, of course, like we were using Fisher representations and so on. This is the data set we used. We had 49 patients, basically. We had 3 classes of data based on the cutoff values of the depression score. So this database was collected based on Hamilton scores, Hamilton interview. 58 moderate to severely depressed, 35 mildly depressed, and 37 remitted. You can also say it healthy patients. Why I call remitted? Because all our subjects started as clinical patients. So 2 different set of results. If we represent these representations, let's say like the frame by frame information, but I need a temporal information. So if we use, for instance, improved Fisher representation, you can think it as having a Gaussian mixture, right? I'm taking a Gaussian mixture of the distribution, and I'm using those to represent what happens through the video, okay, over time. Or we have something called dynamic feature set here. It is looking at explicitly like the speed of change or acceleration of change, like some dynamic features, okay? Hand-coded, like engineered features. And, well, you see that also deep learned features like with stack denoising autoencoders or using the raw landmark moments. You can see the help of deep learning. Also, you can see the help of using this Gaussian representation. But after all, if I use only facial movements, and again, I am not using the full appearance. This is completely based on landmark moments, okay? We can get an accuracy like 72%. If we include head movement in the analysis solely, then it's like 65%, and it's 3-class classification. Head movement is only 3 degrees of freedom head pose, nothing else, okay? Yaw, pitch, and roll rotations, and of course, through the video. And voice is only fundamental frequency and this change turnover time of the interviews. Then we combine, we can go up to 78, 79%. So this was an old study, okay? So nowadays, what we do, instead of using these landmarks, whatever, we would like to use appearance of the face, yes, but it is still a big problem, okay? Based on the ethical permissions and so on. So we focused more on text because text is usable. It is not identifying you. It is open, I can obtain it, and we can easily and automatically transcribe the speech content through the voice files. So this is an ongoing project supported by Turkish Academy of Sciences. What we would like to do here is that at the end, of course, we are going to combine it with the voice. Currently, we are in a stage where we use only textual information, but we have different models. As I said in the beginning, like I'm modeling the text using some emotional representation. Okay, so we get a backbone, which is fine-tuned explicitly for emotion recognition from text. And we, of course, fine-tune it. Additionally, we remodel it to use to represent emotion from text. Then we have another model. We use another backbone, which is fine-tuned for sentiment. And how about to difference emotion to sentiment? Should I go over deep? Like sentiment can be thought as more like mood, okay, like positive, negative. Emotion is more like your responses based on your feelings, right? So happy or angry, whatever. So that's the main difference. And lastly, we also have a generic representation of speech. So this is a nicely trained word embeddings or sentence embedding model, okay? Where I would like to actually get what I have in that speech. And on top of this, so we have the audio data, we transcribe it, auto-transcribe it basically, then we obtain sentence embeddings based on these different models. And then next is, I would like to model them all together, right? So to this end, for each modality, we use a transformer encoder. Transformer encoder structure here is, maybe I'll show it. It's similar to this original transformer encoder, the Vaswani. We have kind of a self multi-headed attention here, okay? So nothing else. So we are trying to learn even a better representation on top of these embeddings through transformer idea. And cool thing with attention mechanisms is that I can measure the importance of the input, right? So in psychopathological assessment, we don't only want to have very good results, we would also like to have the interpretation. Like, where is the depressive behavior? Or like, on which part of this video we see some pattern, and so on. So we would like to analyze such things. Once you go over these transformed features, we have a recurrence modeling, because I would like to have varying length input. I don't want to fix the text like, I'm going to get 10 sentences. Of course not. We are going to get all of them. So we have some RNN structure. Here I just said RNN, but we cross-validate over all different architectures like gated recurrent units or like LSTMs. So it's cross-validated actually. And then through some pooling like max pooling or the last stage pooling of the network, we get a representation. And finally, through a feed-forward set of layers and regression, we output the PHQ-8 score. I'm going to go over next. And recurrence here is important based on the fact that we would like to model temporal dynamics. You use text, voice, face, doesn't matter. Spatial information is important, yes, but temporal information is also very valuable. So you shouldn't lose the link between frames, or you can think it as from one sentence to another. This transition is quite important. You get much more information with temporal dynamics. So this recurrence part is very important. And finally, we regress scores like 0 to 24. This PHQ-8 score means basically outcome of this patient health questionnaire, okay? So 8 questions, each has values like 0 to 3. So max can be 24, minimum can be 0, okay? And basically, if it is higher, you're more and more depressed. Otherwise, you're less and less repressed. Again, this is not a clinical data set, what we use in this work. We use the database of AVEC challenge, like audiovisual emotion analysis challenge. We have these speech transcriptions extracted from voice recordings. In total, like 275 subjects included. Again, indicating explicitly not clinical data. Depression severity annotations in terms of, as I showed, PHQ-8 scores. We analyzed the results in 3 different metrics. We checked the concordance correlation coefficients to see the stability of the estimations, like the correlation of estimations with the actual scores. Also root mean squared error, and also mean absolute error. Why do we do that? Because all different studies use different metrics. We would like to combine these things to compare with as much as possible different studies. And loss in our system, though, is based on concordance correlation. So it's like 1 minus concordance correlation coefficient. Here are some results I included. I said we had 3 different representations, right? These are all text modality, if you look at from that perspective. But in the meantime, from text, I obtained different modalities. If we go for generic textual representation, so you can see that we can go up to a result like the best result there is mean absolute like 3.43 error we have. With emotion only, results are kind of worse. The best there is like 370s. And for sentiment, it is even worse, right? So if you use them separately, it doesn't provide you much stuff. And another interesting thing is we also tried all different layers and so on, but I didn't want to put it here. Like we have these huge tables. Having so many layers is not really helping us because our representations in the first place, they are very powerful. So we generally use like 1 layer recurrence That gives quite good results on validation set. These are all validation results in the meantime. And when we look at like pooling all the representations you obtain from different time steps of the recurrence or just getting the max, at the end, we choose kind of the best validation setup. And we also analyze the importance of the transformer there, right? So because basic idea, okay, so you get a backbone, you inject another transformer structure, then you have some additional layers to learn the final representation. With and without transformer encoder, you can see the improvement. These are quite actually important, like from 3.6 to 3.9 kind of change. These results are already good. Like these are really state-of-art results. When you get close to very good results, it is not that easy anymore to improve. Okay, so but these are significant improvements in the meantime for your information. So we also show that transformer encoders are quite good. And this is a comparison with the literature. So our project right now is in an intermediate step. So we are using only text. We are going to include here like personality. We are going to include here also like the voice signal. Because voice signal and text, when you combine them, if you can model them effectively, it provides you completely different perspective. Think about, I can give the same talk with a completely different voice, for instance, right? So it may be completely different feeling for you. And here we can reach a mean absolute error like 3.99 as test. So it's an unseen test set. And this data set is kind of the benchmark data set. All studies on this topic somehow giving results on this. And again, if you look at the modalities, we only use currently, well, this is wrong. We only use basically text. Voice is shown like this because we convert it to text, but we don't use voice signal, okay, directly. How about deception detection? We have another project, ongoing project. This is supported by TÜBİTAK. It's a 1001 project. Here we would like to use without, like I would like to use computer vision. I would like to use, again, voice analysis. I would like to use text analysis. And I would like to detect deceit. But I don't want to use very special machines for that. So I would like to have an easy setup to understand the deceit. And another thing different in this project, well, I'm not going to show those results in this presentation, but in general, deceit detection is based on classification, like deceitful or truthful. Okay, so I'm going to show some results like this in this presentation. But the aim of our project is having this as a regression task. So we would like to provide how deceitful it is. So we would like to have a range like 1 to 6. And we are trying to say, okay, this speech is like, 1 to 6 is like level 5 deceitful. So this is not really being done earlier. If you go for invasive approaches like PET scans, fMRI, and so on, they are giving you probably best results, but in the meantime, they are not 100% correct and not practical at all, right? So you cannot bring such things to a court, and you cannot decide based on their outcomes in the first place. Ethically, deceit detection is, deception detection is another problem in terms of ethical aspects. But topic-wise, this is an ongoing active research topic. We have a data set, so this is actually an open data set, full of court cases. This is a high-stake deceit detection scenario. So people you see here are in real court cases or in the Senate, they're being questioned and so on. So there will be consequences if they're caught based on lies. So we call such scenarios high-risk scenarios, high-stake scenarios. And what we do, through the videos, we just detect faces, we normalize them, then have the videos of solely focusing on faces. We extract spectrograms of the voice, we also analyze them. We extract text, so the speech content, and we also model them. So visual model and vocal model in this study, this is just recently published study. We use exactly same model because spectrograms are like images after all, right? So if I can convert my voice signal to a spectrogram, then I can analyze it with convolutional idea. Of course, speech model is based on the embeddings, but an overview of the visual and vocal model here, what we use. When you get the image or the spectrogram cut for the specific time duration, so we have a sliding window processing it. We have the stem part of the network. So the stem part is the convolutions where you look at the large picture, right? So with the initial layers of filters, you understand the basics of the image, like the corners, like kind of edges, whatever. And then instead of convolutional layers in this study, we use directly self-attention blocks as convolutional self-attention blocks, not to improve the convolution outcome. Normally you use this headed attention things, and the outcomes are kind of updates your results of the convolution, right? So you can kind of element-wise production of the convolution response and the attention response. We don't do that. Our network, after this stem part, is completely based on convolutional self-attention. So we are using self-attention like a convolution operation. Layer by layer, we have another attention, attention of attention, and so on. We use convolutional attention like convolution, okay? That's the main difference, what we do here. It's a attentional network, you can think. And finally, per time step, if we do that, again, we need a recurrence, of course, for the temporal analysis, and that's it. We apply the same approach for voice analysis too. Instead of facial images, this time we have, for certain durations, in the sliding window, spectrograms, and we feed it to this network. For speech, again, we use Roberta model through some tokenizer for this. We feed the text, and getting the sentence embeddings, word embeddings, we feed it to a feed-forward net and an LSTM network again. Quite straightforward. In this study, we didn't focus on the fusion strategies. We just really went for hard voting and soft voting as like the decision level fusion. So soft voting, basically, if you get the softmax scores, just average them. Hard voting is we are really looking at like what is the class, like deceitful or truthful. Just count 3 different results. If we see 2, we say, okay, it is that class. We also tried actually like low-level concatenation kind of things, or like attentional concatenation and so on. We couldn't even manage to train the system. So processing-wise, training process is quite costly. When you have the video, when you have the spectrograms, when you have the text, and if you would like to have end-to-end training based on the combined data, it is not that straightforward anymore. I don't want to say it is useless to go for low-level fusion. I'm just saying it is complicated. It's getting really complicated to get the nice setup. Because if you're working on deep learning, you know how it is important to, right, get the right setup for your hyperparameters. Again, we use here real-life trial data set. As I indicated in the first place, we have like 121 videos. 7 of them were discarded in this experiment. In many other papers, these were discarded because you cannot detect the faces on those videos. At the end, we have 57 deceptive, 57 truthful trial clips of 50 unique people. These videos are short, generally around 28 seconds. And we go for LOSO, like leave one subject out cross-validation. We get one subject out as test. We use 49 for cross-validating. So like 2 for loops. It's long experiments. Here are the correct classification rates. Of course, this is not clinical data set, so it's kind of easier to reach higher accuracies compared to clinical analysis. Like if you go for deception detection, and if it is high stakes scenario, it is getting easier. So if you go for instance, low stakes scenarios, let's say if you make me believe you after some interview, I'm going to pay you that much. This is low stakes scenario. Okay, so then results are getting less and less accurate because you don't care. I mean, you're much more relaxed and so on. We cannot capture what's happening there easily. Here, based on only facial visual appearance, we can go to 98.3%. Speech is 96 something. Voice is 97. When you all combine these things, this is the thing you can reach. When you get your results very close to 100%, it is not something like, we improved it 1%. But after all, cool thing about this, these are, of course, average results. When we use this on different data sets, like in cross-database experiments, so we train on one data set, we train on our own collected data sets, which are not published yet, then we get much stable, much better results with fusion. If you rely solely on one modality, results are really changing a lot when you change the data set. If you go for multimodality, your results are getting more and more stable. That's another benefit. So these are the results from the literature in the meantime. So these are kind of responses of the self-attention through the videos, like on which frame, on which region of the face is indicating the seat. So that's why these attention mechanisms are nice. We also do this, for instance, for voice, like on which frequency bands you see like the patterns of the seat and so on. Okay, let me check my time. Personality traits. Personality traits, we can represent the personality of a person in different scales, okay? One of the common approaches is to use the Big Five methodology, Big Five personality model, where you have 5 dimensions of personality: openness, conscientiousness, extraversion, agreeableness, and neuroticism. So you have a score for each of these dimensions, and it is a representation of your personality. Okay, so there are data sets for this, and we would like to estimate this. This is quite important in real life because even during a depression assessment, if I don't know your personality, my diagnosis would be problematic. Because some people are in depression, let's say, some people are just like this. They are not in depression. It's their personality. Okay? So actually, expert psychiatrists are also analyzing the personality before the interviews, so they get a better idea. I may be a very, like least openness person, okay? In terms of this openness score, my score would be very, very low. I may not talk, I'm in the mood of like, really not social and so on. But these are also patterns of depression. Or this is also important for job interviews and so on, right? So we would like to have someone open, conscious, extrovert. So these are important things. And companies are also having such automatic analysis for your information. They're recording your interviews. They're getting the statistics of your personality. What we do here is we have also ongoing studies on this, but this one is quite nice study, easy but nice. I would like to just overview it. It's from 2021. Here we look at 4 modalities again. We look at the transcriptions, like what you really talk, voice signal, facial analysis, but we also included the ambient appearance because these are kind of video block recordings from YouTube, and the annotations are apparent annotations. What does it mean? It's not really, the task is here not actually personality assessment, maybe it is apparent personality assessment. Mechanical Turk workers annotated, like for each video, several MTurk workers annotate like how they look, and then we try to estimate their averages, okay? After all, like we use standard backbones, we train them one by one. Like for every modality, we have a specific model first, but then once we have these fine-tuned networks, we concat the features, we put an attention layer on top. So I would like to, through the concatenation, actually before the concatenation, first I have a few layers of network to make them with the same length of the vectors, okay? And then we have for each dimension, for each feature basically, an attention value. So I do kind of soft attention for feature selection, soft feature selection. And on top of this, our loss function is slightly different than standard functions. What you see here is I am getting the average mean absolute value, mean absolute error value for all these 5 different traits, because it's a multitask learning process, right? You regress 5 different scores with a single network. I get the average mean absolute error. And what kind of computation is this? This is the standard deviation of estimation errors of 5 of those tasks. So we have also included in the loss function, and it helps us quite nicely. Why? Because if I decrease the standard deviation of the errors, I'm making my multitask learner much more stable. It is not allowing one task will be, let's say, recognized very good and other will be very bad, just because the average accuracy is nice. I don't want it. I would like to have all the traits, all different traits should be nicely recognized, okay? And it provides me quite stable results. We use Shalearn first impressions dataset. This is a large dataset, 10,000 videos of video blocks obtained from YouTube. And again, labeled with personality factors through Amazon Mechanical Turk. This has a predefined setting, like for training, validation, and test, because it's a benchmark data set too in the literature. It has like 6,000 training videos, so it's quite decent data set to train these models. And here we go again. When you look at the results, that's quite interesting, right? If you look at ambient appearance, what does it mean? Not looking at only face, but also like the whole video, like the furniture, lighting in the room, whatever, the clothing, whole video. You're getting quite good results. You don't even need to do face detection in this tag. So this is important. Of course, this is based on the fact that these are video blocks. So these environments are designed, right? So it kind of represents those people. These are not like on-site spontaneous recordings. They have a nicely designed room, whatever. But this is interesting to us, like, because the first step in behavior analysis, especially if you're going to do face analysis, we detect the faces, we crop the faces, we track them, all these kind of pre-processing, and these are the results. Yeah. So here, with the proposed network and all different studies on the same benchmark data set, like this is also another thing, right? So you're converging somewhere, and after that point, this is not really jumping if you don't change the things very significantly, even with the multimodality. That's the thing. So multimodality is useful mostly, like outcome, before I finish my talk. It is not really about results always, but if you use different data sets, you modeled on some specific data set, and next day that model will be used for real life setup, okay? If you go for cross database experiments, multimodal systems are much more consistent. They're stable, because if you cannot obtain information from one modality, other one covers for the others. So that's the main thing. Always, like in this multimodal talks, you're maybe used to get, if you have only one modality, result is 1, add up this, now it's 2, third modality, now it's 3. Not always like this. If you are getting really state-of-the-art results, they are not improving anymore, but still they are quite beneficial, especially for psychopathological assessments. Because when you change the data, your model reliability changes very significantly. When you have cross-database results, for instance, in this deceit detection, get that training, applied the low stakes scenario, our results went down from 98 to 50%. Okay, so it's significantly changing. Then multimodality starts improving. You start observing the improvements and so on.
Okay, thank you. I think we should applaud our speaker.
Thank you very much.